On the screen now is the situation of the 787 when it was on the runway, about to take off. This is how it works. On the left, we have the fuel cutoff switch, 4-pole dual throw. It's in run position, never moved. The fuel cutoff switch is sending a run signal to relay 1. That goes off to the high pressure shutoff valve. Let's not worry about that now. It tells the high pressure shutoff valve that it wants it to run, and also the EEC has to agree that it wants it to run. So this is kind of like arming the high pressure shutoff valve, ready for the EEC to let it open during engine start. At the bottom here we have fuel relay 2. This one controls the fuel spar valve motor and the bus power control unit fuel cutoff transition signal. So there's again, it's similar to the fuel control switch. These relays are both the same type of relay, 4-pole dual throw, like the switch, 4-pole dual throw. Okay, but the switch controls the relays. The switch doesn't directly control anything, okay? The switch controls relays. So this outlet here, the third one, sends the run signal to this electromagnetic coil in this fuel control relay 2. Okay, so this pulls. When this is energized correctly, current flows through and it pulls a pin, keeps it there, as well as latching force, keeps it there as long as the switch is connected to run. If that switch were to go down to cutoff, due to this switch moving, all of them would move. And it would energize and pull the pin down and turn to cutoff. So either of these coils are designed to pull in that direction or this direction. So the bottom one pulls this way, the top one pulls that way. The insides of the relay may be slightly different to this. It might be pushing instead of pulling, but the point is that's designed to go that way and that one's designed to go that way. It's a dual coil latching relay. So that power for that, the power coming into those coils, it sort of forks here. It's the same power. It comes from none other than the captain's instrument bus. Right now we're just looking at the left side. So think of left is left 28 and center 1. There's another one here, the right side. I haven't illustrated that at all. Imagine all of this in mirror image, but one battery in the middle. Okay, the battery isn't directly connected to that. The battery is directly connected to this. So we're just starting with the left side, and that's all we're looking at right now. So, as I just mentioned, the spar valve through to the start switch, that actually has a name in the circuit diagram. Spar valve start switch control, left engine. That's plugged into or connected to the C1 captain's instrument bus. The C1 captain's instrument bus can get its power from the C1 transformer rectifier unit or from the battery. So the C1, I should go back, the C1 transformer rectifier unit is getting alternating current in from the engine VFSGs and creating 28 volt DC out. So effectively that's only powered if the engines are running. Same said to all of the transformer rectifier units. The other source of power could be the battery, through the battery diode, through the hot battery bus, through a closed main battery relay. And finally, the third source of power could be, if these were to cross-connect, it could actually come from the right side post officer's instrument bus, C2, if this tied together. But during normal operation, this is sending, the bus power control unit is sending a signal to this breaker to stay open and keep isolated. Keep isolated. This is the isolation of the aircraft. Left side completely isolated from the right by that there. This one here remains closed preemptively, provided a bunch of conditions exist, and therefore it is, you can effectively say it's normally closed all the time. Now, just try and grasp where the power sources are coming from here. Control logic to the coils for this, coming from the captain's instrument bus. What else? It's going to the remote data concentrator. The remote data concentrator has 2 inputs, one from the captain's bus and one from captain or left bus via the RPDU-L, Remote Power Distribution Unit L. Okay, so that gets 2 inputs, one from the captain's bus and one from the non-captain's left 28 volt bus. This is not battery backed at all. So think of red as battery backed, able to be powered by the battery, and also able to be powered by the ram air turbine. Think of left as only able to be powered by the engine's VFSGs through the TRU. So for that to be functioning, the engines need to be above about 40 to 50% N2. And by that, I don't mean pressure corrected N2, I mean rotational speed of 40 to 50% N2. Meaning at the ground, as it's rotating, below 40%, this drops off. So above idle and above just below idle, this is all running from the rectifier, from the VFSG generators on the engines. But the brown cannot be backed up by the ram head turbine or the battery. So this RPDU, its job is to distribute power and bring it from either the captain's bus or the left bus. Primarily, some instruments are primarily powered by the left bus. Sorry, not instruments. Some things are primarily powered by the left, and some are primarily powered by the captains. In fact, a lot of things are primarily powered by the captains. I'm just going to flash open on the screen that this is not made up. This is from detailed bus diagrams that I have from the manufacturer. Every single component, and all I'm talking about here is the left side, and I'm just focusing on the parts that are involved in this incident. Okay, back to this. So what we're looking at here, I've got 3 instances. Before anything wrong, during a battery short, and then after battery short and reverse voltage. So let's just talk about the norm here. Nothing should be moving. The Spar valve motor has been instructed to open. It's reached the open state here, and therefore this has a little relay here where it clicks it, it opens it. So this current stops flowing because there's nothing to connect it to here. Okay, so it doesn't stay conducting current. No, it just stops because it hits a stop switch, like a reed switch. There were, incidentally, some issues with these reed switches, and they've got nothing to do with this accident at all. They've since been rectified. The reed switches had some issues in the early days of the 787. So you can see the brown is the non-battery back bus going in here and powering that. So the battery-backed captain's instrument bus does not directly power the fuel spar motor. The engine does, without the battery. So as long as the engine is spinning, it can power the shutdown to go through to shut down this, if that switch moved. That's what happened. So here's the remote data concentrator looking at the status of the fuel control switches. The remote data concentrator gets power again from the RPDU or from the captain's instrument bus. The ARINC remote switch, notice the way I've drawn these together. These are like constantly powered. The ARINC remote switch, or AFDX, some of it is AFDX, some of it is ARINC. Okay, it is powered by 2 different power supplies with a switching mechanism inside it, which dictates which input, and primarily that input is the captain's instrument bus. All the remote switches work the same. So this is effectively turning fiber optic into copper so that the remote data concentrate can communicate via fiber to the common computer network, the common data network, which is known as the common computer resource cabinets left and right, or the whole common core system. Okay, but we're just calling this the network, the switch network. So it's got 2 inputs. Primarily is from there, and secondarily is from there. There is a brief moment of no power during a switching event where it must switch. This is called a remote switch, not because of power switching. That's a network switch. Okay. But incidentally, it also has to flick over from primary to secondary. That little bit of time, lack of 28 volt DC power in the event of a failure, explains why the switches went offline in the ACARS data before the aircraft even left the gate. Well, it had pushed back, started its engines, then it got those ACARS messages. That was this switch resetting due to a momentary loss of power over that bus, as the battery was giving slight issues, and only momentarily bringing down the left bus and momentarily bringing down the right, but not for long enough to trigger the RAT. And also the aircraft wasn't moving, so the RAT wouldn't have deployed. So there were problems on the taxiway before even entering the runway, where the switches were turning off, losing their connection to the common core system, while they would switch over from there to there. They weren't show-stopping because it was able to switch over to there within enough time frame to only log as a maintenance message. This is not a no-go stop fault, unfortunately. So the bus power control units can get power from 3 places. It can get from the left, which continues all the time, get from the battery as long as the battery's working, okay, before the relay, and it can get it from the captain's instrument bus. So this is how everything worked when healthy. Power goes out, down, out through the current return network. Power goes out, down through the current return network. Let's move forward to the stage when the battery is just starting to fail. It can no longer, it's being pulled down to less than 22 volts due to an internal short. An internal short to case is causing the battery voltage to drop down and suck with it the captain's instrument bus. The captain's instrument bus dies. It goes below the required 22 volts. Okay, so the power input to the BPCU left is down. The battery backup is down. The BPCU left is relying on now power from the left 28 volt transformer rectifier unit from all of the engines, which are still happily running. There's nothing wrong with the engines. The battery can bring itself down. It already brings down the bus. When that bus goes down, okay, this battery is not drawing enough current to overpower the built-in logic to stop this breaker, tie breaker, from connecting to try and bring this bus up from here. So what's supposed to happen is when this bus dies, it's supposed to, as long as there's not an overcurrent error on the TRUs, okay, so as long as they're not overcurrent, which is 360 whopping amps, which they were not because this is not 100% short, it's a soft short. So this was brought down below 22 volts. So to bring itself back, it then it let go of the hold open signal that we saw before. So the bus power control unit no longer says stay open, please. It now does not. It closes. And instead of sending power from the TRU to there, the short moves through to here and now brings down C2 bus. This happens after the aircraft has reached about V1. After the aircraft has reached V1, the aircraft has definitely reached 70 knots. When the aircraft reached 70 knots, the main battery relay logic says close for 120 seconds minus 15 seconds for the 15-second countdown of faults. So the logic actually says, once aircraft hits 70 knots, any of the 3 airspeed sensors, once it hits 70 knots, send a one-shot close command to the main battery relay and keep it like that for 105 seconds, and after the 105 seconds, only accept a closure after 15 seconds of guaranteed, only accept an opening after 15 seconds of guaranteed opening. No extra logic to close it. So once the aircraft hits 70 knots, this was going to be closed for about 2 minutes. 2 minutes. Regardless of whether a main battery fault exists. That's written in the logic, it's written in the text. So from the moment they hit 70 knots, that was staying closed whether you like it or not. That's because takeoff is a critical part of flight, and they want battery power available in case something were to go wrong with the engines or the transformer rectifier units. So they have programmed it to not inhibit the battery from powering this bus within 2 minutes of hitting 70 knots on the takeoff run. So what's happened here is the battery's shorted, the main battery relay has been forced closed by that countdown, and the short circuit has made its way through a failed fucking battery diode module, which is the very reason in the first place that the battery was broken. Current shouldn't be able to flow backwards, but because the failed battery diode module is broken, it flows through here, it backflows through here, shorts to ground, brings the bus down, closes the bus tie contactor, shuts down the second bus, and the rat drops out. Just before the aircraft actually leaves the ground. Just after V1 and just before actual rotation. It's at the call of VR rotate. Just as they pull back. It's too late. The rat drops out. It would have been a strange experience for the instruments to die right on rotate. They might have said something about it, but we haven't been told anything about it in the report, the preliminary report. That may be what they said when they said, why did it cut off? I didn't do it. So at this moment, everything else is just sitting at rest. There's no power flowing through this coil. The latching relay is holding it latched at run. No power is flowing anywhere in that relay. Nothing's happening. The RDC stays live thanks to the outer left 28 volt. The BPCU stays live thanks to the outer. But this circuit just stops conducting electricity altogether. There's no current flowing anywhere. This continues on for as long as the battery takes to completely melt apart inside. When it melts apart inside, a few things happen. Firstly, things go extremely high current, and some of the straps across chains of the battery melt and open. Then the battery melts across from one side of the case to the other, creating like a reverse voltage within the case, and then cell 6 shorts across to the case just like it did in Takamatsu, and you end up with reverse voltage. I'm going to bring that up. This here is the Takamatsu event battery, the report about the battery failure. And I've drawn in the diode module, I've drawn in a bunch of stuff, but in that hazy red in the background was the path of the fault current from the Takamatsu event. Cell 6 shorted to the case, which caused everything to just collapse. In this case, we actually had one of these bars break. One of them melted through. That happened in Takamatsu as well. One of them opened up, and this side swelled and pushed across, or used the monitoring cables from the monitoring, and it was able to connect that to that. And what you have here is a fight between TRUs and battery. So this is putting out about 18 volts of reverse current. It could be anywhere. It could even be here. It could have been that, which is more than 18, to be 18 plus another 4. The relays do not need a full 18 volts to actuate. They need 14.5 volts according to military specifications. I'll open that proof for you now. Here's the KL leach relay. Okay. As per military specs, 28 volt relay, specified latch reset voltage is 14.5 volts. So all we needed was this battery's fight to be at least 14.5 volts compared to the TRUs, which were now in overcurrent shutdown mode, and you have reverse current going out through the ground strap, which takes 1.5 minutes to burn through, according to the Takamatsu event. The ground strap is so big it stays there. The current flows out of the positive, through the battery case, through the ground strap to the current return network, takes the long route back through the captain's instrument bus, through the run coil backwards, through the shorted battery diode module, back through the contactor, which is fucked and never worked properly, back through the positive terminal, across the negative, and to complete the circuit and to start again. This is your source of negative voltage. Whatever dirt in this was, whatever dirty voltage was present, it was kept smooth by the capacitors in the fuel cutoff circuit, which incidentally are not part of the relay. They are part of the P300 and P400 cabinets. Okay, back to the diagram. So what we're looking at here in the middle is the stage before it reversed. Now that the battery is reversed, what happens? Current is able to flow the wrong way. From the battery down to the current return network, out here, back through the current return network, up here, through the run coil. Okay, the switch hasn't moved from run. The current flows backwards. Through the relay, through the coil backwards. What did the specification sheet about the relay say? Relay will not be damaged by applying reverse voltage to the coil, although the relay may transfer. So what that means is the relay is going to push instead of pull. So the switches, instead of being like this, instead of being like that, they rotate and go like that. Now, we've connected this 28 volts from the left bus system, which is still running. The engines are still putting out, AC power. That bus is still functioning. That bus is still functioning through here, sending it through the fuel shutoff motor. There are 2 windings through to CRM. Okay, you might say, oh, Jeremy, you said the CRM was reverse current. Each circuit is its own, sharing the same copper conductors of the current return network. It's not all back to the battery. This is its own circuit. Anything that's supposed to work from that will still work. It's just sharing the same current return network. Its source of 28 volts is different. It's not the battery and it's not the TRU. It continues to function sharing the same copper bus, the copper ground bus. Okay, so this is what caused the engine to shut down. Then the 15-second countdown for main battery relay opened up, and I haven't illustrated this, but everything then reset and goes back to norm. This resets, fuel flow starts flowing again. This opens up, and the aircraft tries to climb. But instead, it just flies faster into the buildings, as said by your surviving passenger. There we go.